So let's talk briefly, kind of give a 50,000-foot view of some of the POSA patterns that are used in Android and in Java's concurrency frameworks. So again, there's a number of classic books on software patterns, and there's the Gang of Four book, which we'll talk about those patterns in a minute too. Those patterns are typically not as widely used for the basis of structuring concurrent programming in applications. They're used for other purposes, but concurrency wasn't really a big emphasis in the time of the Gang of Four authors. In fact, at the time that the Gang of Four authors wrote their book, which was the early to mid 90s, there really weren't a lot of programming environments or platforms or frameworks or libraries that supported multi-threading. So perhaps it's no surprise that their book didn't really emphasize that, because that wasn't something people were doing commonly. So it was hard to know what the patterns were to write concurrent code. When I started doing my work, which was the mid 90s to the 2000 timeframe, that resulted in some of the POSA patterns, I was focusing on concurrent programming. And so I was documenting and discovering and codifying patterns for concurrent programming. So we'll talk about those first. And you can take a look at this link if you want to learn more about the POSA book series. So again, here's just kind of a recap. There's a bunch of different Android and Java frameworks or mechanisms that handle concurrency, things like loopers, the Hammer framework, the Java Executor framework, which we've talked about at length, the Android async task framework, Java linked blocking queue, Java streams, and these different frameworks are realized by a number of patterns. In fact, there's often many patterns, but the ones that are kind of most architecturally significant here would be things like thread-specific storage for the looper, and the command processor and active object pattern for the Hammer and Java Executor framework, Half-Sync async for async task, MonitorObject for linked blocking queue, pipes and filters for Java streams, and so on and so forth. And again, as I've sort of alluded to before, it's really reassuring to know that, number one, these patterns that are documented that we teach you in other contexts are actually used in practice. That's really good to know. And it's also good to know that people who develop these very useful and efficient and robust concurrency environments and frameworks were aware of these patterns, whether they knew them as patterns when they wrote the code or not. They use them because they're time-honored ways of resolving common challenges that arise when you build software in a particular context, like concurrent application environment. So let's just go over a couple of the patterns real quick and give you a high-level view of what they're about. And then throughout the rest of another week or so, we'll go through each of these patterns in much more detail and explain to you what the pattern's about, and then show very concrete realizations of said patterns in the context of Android or Java. So the first pattern we're going to talk about is called thread-specific storage. And this pattern allows multiple threads to use one logical and global access point to retrieve an object or objects that are local to a thread. Even though they look global, they're actually local to a thread, and therefore they don't actually incur any locking overhead each time that thread accesses the object that resides in thread-specific storage. And this is a POSA 2 pattern. It appeared in the book I wrote in the 2000 timeframe. You can also read about it in a paper that's linked down below at my Vanderbilt account. And this is sort of a preprint of what's in the book. The way that this pattern works is essentially every thread, there's a data structure of some kind. There's various ways to do this, but logically you can think of there being a data structure that each thread has, and think of it you can either think of it like each thread has an array-like construct, or you could think about there being sort of a global two-dimensional array that all the threads share, but the contents of that two-dimensional array are indexed by thread. So each thread keeps track of one, say, column, if you will, in this two-dimensional table. And all thread-specific objects will be managed out of that unique to the thread column, or that unique data structure. And so what happens is you have these thread-specific objects, which in every thread have the same ID, thread local object or thread specific object 1, thread specific object 2, and so on. And every thread uses the same ID to indicate its object, but each thread has its own unique copy of the object, so which is never shared with other threads, and therefore there's no shared mutable state to have to synchronize. Now, this particular pattern, we'll talk more about this pattern later, but this particular pattern is used in Android with something called the looper. And the looper is essentially a data structure that is used to have essentially active objects or command processor-like objects. And you can feed messages into the looper, and then that looper will have a queue, and it'll queue up the messages, and it'll go ahead and process the messages within a single thread. And again, we'll talk more about that later. It corresponds to the command processor pattern or the active object pattern and so on. And the way this works is the Android implementation of looper makes use of thread local storage, which is something provided with Java, in order to ensure that there's only one looper object per thread. And so it's a very clever way of synchronizing or not having to synchronize access to the one and only looper object per thread. And we'll look at this in more detail. So it makes things very efficient because there's no need to acquire a lock to access the looper in the looper thread. And that's because there's no shared mutable state. So there's no need to lock anything. Another pattern, which is kind of used in conjunction with what we just talked about, but of course is its own pattern in its own right, is something that's called the command processor pattern. This is a pattern that appeared originally in the POSA 1 book. I was not an author on that, but these were my colleagues who I worked with on other books. And this particular pattern packages a piece of application functionality in the form of an object. And then it makes it possible to execute this functionality in some other context, such as a later point in time, or in a different process, or in a different thread, and so on and so forth. And so basically what we're doing here is we're taking the concept of commands, which was documented in the classic Gang of Four books, command pattern, and then we're allowing these commands to be queued up and then processed by other threads or other processes, depending on whether you're running on the same machine or a different machine. And so it kind of looks like what's shown in this diagram down here, where you create these objects, these command objects, you give them to the command processor, and then they're executed in one or more threads of control in the background. And this particular pattern is what guides Android's Hammer framework. So Hammer stands for handlers, messages, and runnables. And we'll talk more about that. That's a very fundamental concurrency framework that's used in Android for all kinds of things. Most commonly, it's used to be able to do processing in background threads and then pass the results of that processing to the one and only user interface thread, which runs in the foreground and interacts with the user. So we'll see that what you can do with the command processor pattern as used in Android is be able to pass messages back and forth between threads in order to be able to have computation done in one place and then typically display done in the user interface thread. There's another pattern, which is, you can think of it as kind of the command processor pattern on steroids. The command processor is really about message passing. You're passing these messages around between handlers, and those messages then can be run in a different context. There's another pattern, which is also a POSA 2 pattern, which is called the active object pattern. And this is a very, very important pattern. It's used as the basis for lots of concurrency models. For example, the actor model, which is very popular in certain functional programming environments like Akka or Scala and so on. And what this pattern does is it defines service requests on components or objects as the units of concurrency and runs the service requests on a component in different threads from the thread that invoked the request. And what's important to recognize about this relative to the command processor pattern we just talked about is that instead of creating messages and passing messages, instead you make method calls through proxies, and these proxies then convert the method calls into messages and then deliver these messages to a pool of threads, and then the messages are turned back into method calls that are invoked on the implementations of the objects, typically in a different context, like another thread or another process. And so the thing about this is it looks a lot more like you're making method calls, but in fact, you're really transferring the state of parameters from one context to another, where they're invoked back as method calls on the receivers. And this is used in a bunch of places. The Android has this Hammer framework, which supports both message passing as well as method calls. And that's something that's also provided with the active object pattern. And it's also worth pointing out that Java's executor service framework applies this pattern to enable two-way callables to execute in a thread pool. So you can have one thread where you're submitting work by calling submit, and then there's another place where that's processed. And that, again, is really sort of more like an active object pattern approach. And you get back something called a future. And the other thing that makes the active object model different from the command processor model is it can support two-way communication, whereas the command processor pattern is really used for one-way communication. And what makes the active object model interesting, or the pattern interesting, is that the way you get results back from this two-way asynchronous communication is by using something called a future. And believe it or not, future is also a pattern. We won't really cover it in detail as a pattern, but when we talk about the active object patterns implementation, you'll see that futures are important capacities and important roles in that pattern as well. And that underscores a very important point about patterns. They're typically used together. They don't just appear by themselves. They like to congregate. They're very social. They enjoy interacting. Another pattern that we'll spend a little time on, fascinating pattern, is called the Half-Sync, Half-Async pattern. And this pattern is used to decouple synchronous and asynchronous processing by having two different layers, one of which is the async layer and one of which is the sync layer. And they simplify programming without degrading performance through the use of a queuing layer. And this pattern is also a POSA 2 pattern. It's documented in a link at the bottom of the slide. And this is what's used by Android's async task framework to process tasks in background threads, which can run synchronously. They can block, and then they publish the results back to the user interface thread, which, very important to understand in Android, can't block for very long. And so this pattern, again, is used to structure the way in which the async task is designed in Android. Yet another pattern that we'll look at, because this is a cool one, we've talked about this before, is the MonitorObject pattern. And this is also a POSA 2 pattern, which you can read about at the link at the bottom of the slide. And it's used to synchronize concurrent method execution to ensure that only one method at a time runs within an object. And it also allows the object's methods to cooperatively schedule their execution sequences. So, of course, this should sound very familiar because this comes built into Java, and Java objects are inherently monitor objects, although admittedly somewhat simple-minded monitor objects because of some of the limitations of Java built-in monitor objects, for example, only having a single monitor lock, only having a single monitor queue. But for that reason, you can also use other Java synchronizers like reentrant locks and condition objects in order to build more scalable and more flexible and efficient monitor object implementations by using the building block synchronizers that come out of Java. Java's linked blocking queue applies this pattern to implement a very efficient synchronized blocking queue. And what it does that's so clever with this is it actually has a pair of locks and a pair of condition objects. And those pair of locks are used to differentiate or decouple threads that want to put things on the queue from threads that want to take things off the queue. And so it's a really cool and efficient implementation. And we'll actually walk through that implementation in some detail because it's really worth understanding how it works under the hood. Yet another pattern that's supported by mechanisms in Java and Android is the pipes and filters pattern. And this is a pattern that appeared in the POSA 1 book and is used to divide the tasks in an application up into multiple self-contained data processing steps, and then connect these steps together via intermediate data buffers to form a data processing pipeline. And you don't always need buffers, but you need to be able to pass messages through the pipeline. And so you can take a look here if you want to learn more about this pattern. This is a description of the pipes and filters pattern. There's also a version that appears in the POSA 1 book, which you can see here. And this pattern is what's used by Java Streams framework in order to be able to implement both sequential and parallel streams by being able to have all these so-called aggregate operations that can be chained together to make a pipeline that will transform and or filter requests that come through the stream. And it's also worth pointing out that this type of model is also used with modern reactive streams environments like RxJava or Project Reactor, which also implement other common patterns like the publisher subscriber pattern and the iterator pattern. So you can take a look here and find more information about all this stuff.